There is a university on the south side of Chicago where, at the end of the 1970s, a young paleontologist was finishing a piece of work that had taken him most of a decade. He had not spent it digging, he had spent it reading. Jack Sepkoski was assembling something that had never existed before, a single list of every family of marine animal ever found anywhere in the fossil record, with the moment it first appears and the moment it stops. A family is a broad grouping, the scale of the cats or the crocodiles or the sea urchins, not individual species but the branches they hang from. He went through the published literature one paper at a time, one journal at a time for years, and he wrote them down. Years of a man's working life ending as a stack of paper you could carry under one arm. By 1982, the list was long enough to do something with. Sepkoski and David Raup, a colleague at the same university, laid it out across the whole span of the fossil record and looked at where the losses gathered. Extinction, as it turns out, is always happening. There is a steady background to it, a slow attrition, families disappearing quietly in every interval anyone has ever measured. What Raup and Sepkoski wanted to know was which moments rose so far above that background that ordinary attrition could not account for them. So they ran the statistics, and they drew a line. 4 events cleared it. The end of the Ordovician, the end of the Permian, the end of the Triassic, the end of the Cretaceous. Those 4 rise above the line and stay there, and no one has seriously argued with them since. And then there is a sentence in that paper which almost nobody has read. It sits in the abstract, in the opening paragraph, the part everyone skims on the way to the figures. It reads, "A 5th extinction event in the Devonian stands out from the background, but is not statistically significant in these data." Not significant. In the study that gave the world the Big Five, the 5th one did not clear the line. It went onto the list anyway, and it has been taught as one of 5 in every textbook and every documentary since for more than 40 years. A threshold is a useful thing to have. It is also, unavoidably, a decision. Set it at one height and 5 events come through. Set it a little lower and you get a dozen. Set it lower still and the whole idea of a separate category starts to dissolve back into the ordinary business of things ending. The line was not wrong. It did exactly what it was built to do, which was to ask a narrow question honestly and answer it honestly. But it had an effect that nobody intended, and the effect was this. The events underneath it stopped being counted, and a generation after that, they stopped being taught. They did not stop having happened. There are somewhere around 35 of them in the recognized record, and the exact number depends on which of the disputed ones you allow in. We will be careful about that as we go, because several of them are genuinely argued over by people who know the rock well. Some are as severe as anything on the famous list. A few are worse. They begin long before there are fossils to count. The first one is more than 2 billion years old, and the strangest thing about it is that the poison was a waste product, something alive making it without any idea what it was doing for hundreds of millions of years until the world ran out of places to put it. From there the record runs down through frozen oceans and drowned forests and seas that quietly stopped holding oxygen through the famous events and past them, all the way to a bird that died in a cage in Cincinnati on the 1st of September 1914, and past her into the counting that is still going on tonight. There is a second thing the line did, and it is harder to see than the first. It taught us to weigh these events by how many died. 90% of species in one case, 3 out of every 4 in another. Those are the numbers printed under the pictures, and they are real numbers, carefully arrived at and worth having. But there is another way to weigh an emptiness, and the rock keeps it just as faithfully. Not how many died, but how long the world stayed empty afterwards. How long before the reefs came back? and how long before anything on land grew large again. Measured that way, the order changes completely. The event that killed the most is not the one that left the longest silence, and two of the longest silences in the entire record belong to collapses that never cleared the line, and so were never counted, and so were never taught. If you have ever been told that there are 5 mass extinctions, you were told something that was true of a graph, and not quite true of the Earth. What we hold when we sit with a record like this one is something the planet never meant to hand over. It does not keep these events on purpose. It keeps them the way a floor keeps dust, by being slow and by being in the way. Every one of these endings happened without a witness. There was no one to see the last of anything, no one to write down the date, nothing at the time that understood a world was closing. The record was made of mud and left where it fell. And somehow, out of all of that, a species a few 100,000 years old has worked out how to read it, and now argues about where to draw the line. That is an odd thing for an animal to do. We seem to need to know what came before us, including the parts that would have killed us. Before we walk back that far though, if you find yourself drawn to these slow descents into deep time, consider subscribing to continue these journeys with us. There is a great deal in the Earth's record that never made it into the textbooks, and a great many quiet nights left in which to go through it. And let me know in the comments where you're listening from tonight, your city, your time zone. It's always something to see how far these journeys travel, all of us awake or half awake in different corners of the same old planet, listening to the same long story. Now, let's begin our journey at the beginning of the record, which is not an asteroid and not a volcano, but something far quieter and much harder to see. 2.5 billion years ago, the Earth was poisoned by the things living on it. They had been at it for hundreds of millions of years by then, patiently, in enormous numbers, without any way of knowing. The poison was oxygen, which is the first difficulty with this story, because oxygen does not sound like a poison to anyone who happens to need it. You are using it now. It is in the blood behind your eyes, in the muscle of your heart, in every cell currently doing the work of keeping you here. And there is nothing about it that feels like a threat. But there was a world before this one, and it ran on chemistry that oxygen takes apart. Rusting and burning are the same process running at different speeds, and what happened to the early Earth was a very slow fire that took 1 billion years to catch. For most of its early history, the planet's air had almost no free oxygen in it. There was nitrogen, there was carbon dioxide, and there was a great deal of methane, a far more powerful greenhouse gas than carbon dioxide, and probably the thing doing most of the work of keeping the world warm beneath a young sun that shone measurably fainter than ours does. The oceans held something they could not hold today. Iron dissolved right through them in quantities that would be impossible in any modern sea. Iron will not stay dissolved in water that has oxygen in it. Put the two together and the iron comes out of solution, rusts and sinks. If you want to see the organisms that changed this, you can. There is a shallow, over-salty bay on the western coast of Australia where the water is too briny for the snails and worms that would ordinarily graze such things flat, and in the shallows of that bay there are low domed mounds sitting in ankle-deep water, dark and rounded, like a paved floor that has gone quietly wrong. They are built by cyanobacteria, bacteria that photosynthesize, layer on sticky layer, trapping sediment as they grow, rising perhaps 0.5 millimeter in a year. Their ancestors were doing precisely this, in shallow water very much like it, more than 2 billion years ago. The method has never been improved on. It did not need to be. What they do is take light and water and carbon dioxide and make sugar out of them, and the leftover is oxygen, on one mat that is nothing at all, across every shallow shelf on a planet, sustained for hundreds of millions of years. It becomes the largest chemical event in the history of the world. and for most of that time, none of it accumulated anywhere. It was consumed exactly as fast as it was produced, and the thing consuming it was the iron. The result is one of the most beautiful rocks on Earth, and there is a fair chance you have picked up a polished piece of it in a museum shop without knowing what was in your hand. Fine alternating bands, dark grey and deep red, sometimes a millimetre apart and sometimes the width of a palm, running metre after metre through cliff faces in Western Australia, in Minnesota, in Brazil, in Ukraine. Each band is a layer of iron that came out of the water and settled. The whole formation is the record of an ocean rusting, written down in order, and we dig it up. Banded iron is where most of the world's iron ore comes from. The beams in the building around you, if it has any, the body of the car outside, the hull of every ship afloat tonight, nearly all of it was lifted out of a chemical catastrophe that finished before there was any animal or any plant of any kind. Sinks fill. That is what sinks do. Somewhere around 2.5 billion years ago, the ocean's dissolved iron began to run out faster than the planet could replace it, and for the first time in the history of the world, there was oxygen left over with nowhere to go. It went into the air. What happened next cannot be counted, and that deserves saying plainly here, because it sits underneath everything that follows in this record. There are no bodies. There is no layer of small skeletons to measure. No drop in the number of families. Nothing that died in this event and left behind anything we could identify as itself. What we have instead is chemistry, and the chemistry is unambiguous about the change while staying completely silent about the cost. Sulfur in rocks older than this behaves in a way it simply does not afterwards, and the only explanation anyone has made work is the arrival of oxygen high in the atmosphere. Riverbeds older than the change carry rounded grains of fool's gold and other minerals that oxygen destroys on contact. After the change, those grains stop turning up because they no longer survive the trip downstream. Rocks begin for the first time to turn red, so we know the air changed and we can date it to within a few tens of millions of years. What nobody can tell you is who it killed, or how many, or how fast. Any percentage quoted for this event is a guess with a decimal point attached. What can be said is where the survivors went. The anaerobic world was not erased, it was pushed. Out of the sunlight, down into the sediment, into hot springs and stagnant deeps, and every pocket of the planet where the new gas could not follow. It is still there. It is in the mud at the bottom of ponds, in waterlogged soil, in the black layer a few centimeters beneath a tidal flat. And a considerable quantity of it is inside you, in your gut, in an environment kept carefully free of the very thing you are breathing. The losers of the first catastrophe on Earth are living in your body, and from their point of view, you are a refuge. This is also where the record starts teaching us how it wants to be read. If the dead cannot be counted, the question has to change, and the question the rock will actually answer is a different one. How long did the world stay changed? For this event, the answer is hard to hold in the head. After the air filled with oxygen, the carbon locked into the world's limestones goes strange and stays strange for an extraordinary length of time, shifted in a way that only happens when enormous quantities of living material are being buried instead of allowed to rot, which is another way of saying that oxygen was being made and not spent. It is the longest signal of its kind anywhere in the planet's history. How long it ran depends on which dating you trust, and the honest range is somewhere between 130 million years and 250. Sit with either end of that. At the short end, it lasted about as long as there have been flowers on Earth. At the long end, it lasted longer than there have been mammals. There is one further consequence, and it is the reason the story does not simply stop with a change of air. Methane and oxygen cannot share an atmosphere. Put them together, and they react, and what comes out is carbon dioxide and water, both of which trap heat, and neither of which traps anything like as much as methane. The Earth had been kept livable under a dim sun by a greenhouse made largely of a gas that oxygen destroys on contact, so the thermostat failed. Not quickly. Nothing in this part of the record is quick, but thoroughly, and the ice came down. Geologists call the glaciations that followed the Huronian after the rocks along the shore of Lake Huron, where they were first read out of the ground. There were at least 3 of them, and there is reasonable evidence that one reached the tropics, which would make it the first time this planet ever froze from pole to equator. We are working here at the outer edge of what the rock is willing to tell us, and the details are argued over by people who have given careers to them. But the shape is not in dispute. The world made oxygen, the oxygen ate the greenhouse, and the greenhouse had been the only thing standing between a faint sun and a white planet. The cold stretches and the warm gaps between them, taken together, ran for something on the order of 300 million years. Then it ended, the ice went back, and the Earth, having frozen for the first time, did not freeze again for another 1.5 billion years. In the Flinders Ranges of South Australia, a boulder sits in rock that was once the soft floor of a shallow sea, and it has no business being there. Everything around it is fine mud, settled grain by grain in water too still to move anything heavier than silt. The boulder is astray, and directly underneath it the mud layers are bent, pressed down and splayed out sideways the way a mattress dents under a knee, then buried by the layers that came afterwards and held the dent exactly as it was. Something dropped that stone from above. In water that quiet, there is only one thing that carries a boulder out to sea and then lets go of it, and that is ice. Geologists call these drop stones, and on their own they are unremarkable. The Baltic is full of them. What is not ordinary is where this ground was sitting when the stone came down, and where the same kind of ground was sitting in Namibia and Scotland and Canada and Brazil. When those muds were being laid, several of these places were within a few degrees of the equator. So there was floating ice at the equator, not on a mountaintop, at sea level, carving boulders into a tropical ocean. How anyone can claim to know where a rock was sitting 600 million years ago is worth a moment, because the entire picture rests on it. As fine sediment settles, magnetic grains in it swing into line with the Earth's field like small compass needles, and when the sediment hardens, they are locked in position. Near the poles, the field comes down almost vertically. At the equator, it runs nearly flat. Measure the angle at which those grains froze, and the latitude comes out of the arithmetic. It is delicate work. Rocks get reheated, remagnetized, tilted and folded, and separating an original signal from a later one is the sort of problem that has produced long careers and longer arguments. But the low latitude readings have now survived 4 decades of people trying very hard to break them on several continents, and the simplest explanation still standing is the uncomfortable one. There were 2 of these freezes. The first began around 717 million years ago and did not let go for roughly 56 million years, very nearly the whole span that separates us from the last dinosaur. The second came later, beginning somewhere after 650 and ending at 635. That world is easiest to describe by what it lacked. No rain fell anywhere, so no rivers ran down to the sea. There was no surf, because an ocean with a lid on it does not make waves. The water cycle, the loudest process on the surface of this planet, and the source of very nearly every sound in the open air, more or less stopped. What remained was wind moving over ice and dust, and the slow grinding of glaciers wherever the ice lay thick enough to flow. Ice that covers a planet is extremely difficult to remove, because ice is white, and white returns sunlight to where it came from. The more of it there is, the colder the world gets, and the colder the world gets, the more of it there is. Once that is running, nothing at the surface can interrupt it. But the surface is not where the planet keeps its thermostat. Carbon dioxide comes out of volcanoes, and volcanoes are driven by the heat of the interior, which neither knows nor cares what the sky is doing. It kept coming out, and the thing that normally takes it back out of the air, rain falling on rock, dissolving it slowly, washing the result down to the sea, had stopped entirely. So it gathered. For millions of years, with nothing to remove it, carbon dioxide accumulated in the atmosphere over a frozen world, until there was enough of it to overpower the ice. And then the same feedback that had sealed the planet ran in reverse. Every patch of dark water that opened absorbed heat instead of throwing it back, which opened more water, which absorbed more heat. The rock records the flip with almost no transition in it at all. Sitting directly on the glacial rubble, in section after section around the world, is a layer of carbonate, the kind of rock that forms in warm, shallow tropical seas. Cap carbonates they are called, ice debris, and then warm water limestone laid straight down on top of it with nothing in between. The world changed states faster than the seafloor could record anything in the middle. How much of the second freeze was actually ice is being revised as the dating sharpens. Older estimates allowed as much as 16 million years. Recent radioisotopic work argues for something nearer 4. That difference matters more than it sounds. 56 million years under ice is a filter that almost nothing gets through. 4 million is a hardship. If the second freeze really was the shorter one, it may be part of the reason the world that emerged from it was capable of what it did afterwards. Which leaves the question the whole thing turns on. How does anything live through this? Some of the answers are very small. On glaciers today in Antarctica and Greenland, a grain of dark dust settling on ice absorbs sunlight, warms, and melts its way down into the surface, leaving a narrow cylinder of meltwater a few centimeters across. Bacteria and algae live in those cylinders. A single ice sheet carries millions of them. That is one of the possibilities taken seriously here. A planet's worth of life getting through in 100 million separate ponds, each of them roughly the size of a teacup, each one open to the sky. Others are underneath. Where the ice thinned, light came through it. Around volcanic vents on the seafloor, heat kept water moving whether or not the sun ever reached down that far. And one of the answers is not a hypothesis at all. In southern China, there are black shales lying sandwiched between layers of glacial rubble, and pressed flat into those shales are seaweeds, bottom-living, photosynthetic, unable to do anything whatsoever without light. Which means that while the ice was on the world, there was somewhere with open water and daylight coming down into it, and something green growing on the floor of it. Later work has pushed those livable stretches further than anyone expected, out into coastal water at middle latitudes, at least during the long thaw at the end. Exactly how much open water there was, and where and for how long, is the live argument in this corner of the science, and has been for 25 years. There is a version in which the ocean sealed shut from pole to pole, and a version in which a belt of slush and open sea held on around the middle of the world, and the honest position is that nobody yet knows which to believe. What can be said is that the evidence has been drifting steadily toward a planet leakier than the name suggests. Stand on that ice, out over the tropical ocean, and the world is white to the horizon in every direction you turn. The sun is up, and nothing is melting. There is no sound but wind, no smell at all, and no visible reason to believe anything on this planet is alive. And under your feet, somewhere down there in the dark, something green is holding on in the last of the light. There is not very much of it, and there does not need to be. It only has to last as long as this does and still be there when the water comes back. When the water did come back, it came back into a world with an extraordinary amount of room in it. And on the floors of those shallow, newly warm seas, in the mud, in the low green light, spread out flat and going nowhere, something began to grow that nothing before or since has quite repeated. Nothing on that seafloor was chasing anything. Nothing was fleeing either, and nothing at all was digging. The mud lay exactly where it had settled, layer resting undisturbed on layer all the way down, because there did not yet exist anything with the habit of turning mud over. Across the top of it grew a living skin, bacteria and algae bound together into a tough, continuous mat, covering the seabed the way turf covers a field, so that the join between water and sediment was not a soft gradient, but a surface that could be peeled up in sheets. The water above held nothing worth calling a swimmer, and the organisms themselves, the ones this whole stretch of time is named after, did not move. They were flat, most of them, and quilted. The commonest design is a frond, a leaf-shaped body split into branches, with each branch split the same way into smaller branches, and each of those split again, the pattern repeating down to the finest scale the rock is able to hold. Some were the size of a thumbnail. Some ran past a meter. They stood upright on the mat or lay pressed against it, and they stayed where they were. And as far as anyone can tell, that was the entirety of their behavior. Many of them, including the largest and the strangest, have no mouth, no gut, no opening of any kind, nothing that could take anything in. Whatever they lived on came in directly through the surface of the body, absorbed out of the water or out of the mat beneath them, which is why the branching design matters more than it looks. A shape divided and subdivided like that carries an enormous amount of surface for the volume it wraps around. These were bodies built to soak. The place where they were first recognized sits in the same range of hills that holds the glacial rubble, a little higher up in the same stack of rock, so that the ice and what followed it are stacked one above the other and can be walked through in an afternoon. In 1946, a geologist named Reg Sprigg, working for the South Australian Survey, was sent to the abandoned Ediacara minefield in the Western Flinders Ranges to judge whether anything down there was still worth digging out. He turned over slabs of sandstone and found impressions on their undersides, round, disc-shaped, faintly rayed. He thought they were jellyfish. He called them medusoids and published within a year, and it was the natural reading, the one almost anyone would have arrived at. Here were the remains of familiar creatures, extremely old but recognizable. They were not jellyfish. It took decades of argument to establish that a good many of these organisms do not sit comfortably inside any living group at all, and that argument is still running. Some are probably early animals, others may be something else entirely. A form of large multicellular life that was attempted once on every coast in the world and then not attempted again. What Sprigg had turned over was not the opening of the familiar world, it was the closing record of a different one. They hold their place in the rock for something like 35 million years in assemblages found in Newfoundland and Russia and Namibia and Australia, and then they are gone in 2 stages rather than one. Around 550 million years ago, the richest communities, the ones carrying the widest range of body designs, thin out sharply, and only a reduced set carries on into the final stretch. At the boundary itself, roughly 539 million years ago, the remainder go too. What makes this unlike anything else in the entire record is what is absent from the rock around it. There is no ash layer and no iridium, no lurch in the carbon that would mark the ocean's chemistry failing, no glacial debris, nothing to suggest the world turned hot or cold or acid. By every measure a geologist can take, the layers above and the layers below describe the same planet. An entire grade of large organisms, present on every seafloor anyone has examined, holding station for tens of millions of years, and then simply absent, with nothing in the surrounding rock to hold responsible. Except that something was arriving. It is small, and against the scale of what it did, it is easy to walk past. In rock from that same interval, in China and Namibia and Brazil, there is a tube-shaped fossil called Cloudina, the earliest animal known to have built itself a mineral shell. In one collection from Shaanxi province, out of more than 500 tubes, roughly 1 in 40 carries a neat round hole. The holes are minute, under 0.5 millimeter across at the widest, and finding them takes a lens. They are also not random. The size of each hole tracks the width of the tube it was drilled into, which means that whatever made them was selecting what to attack. That is the earliest apatite anyone has found in the fossil record, and it does not look like apatite. It looks like a hole in a shell made by something too small to see, that was nonetheless choosing. At the same time, the mud begins to change. Traces appear in the sediment, shallow to begin with, horizontal, barely more than furrows, and then deeper, then vertical, then branching. Something had started to dig. A burrow is a small thing to set against a planet, but the mat was the world. It was the floor those organisms stood on, and fed through, and were preserved by, and it worked only so long as it stayed continuous. Punch through it often enough, and the sealed skin becomes a churned, oxygenated, endlessly reworked layer of soft ground, which is the seabed every ocean on Earth has had ever since, and none had before. Stand on that sea floor a few million years earlier, and you are standing on a floor, firm, sealed, quiet, with a fixed community rooted into it, and almost nothing in the water overhead. Stand on the same patch afterwards and the ground gives under you, turned over and worked through by animals too small to see, while the water above has begun to fill with things moving on purpose. Nothing arrived from outside in between. The world acquired apatite, and then it acquired diggers, and the old arrangement had no answer to either. There is a complication here, and it is genuine rather than technical. The mat is also the reason we can see any of this. Soft bodies do not normally survive as impressions in sandstone. They survive when a mat holds the shape in place, long enough for sediment to cast it. Destroy the mats, and the only window this kind of organism has ever been visible through closes. So some portion of what reads as a disappearance may be a shutter coming down rather than a death. And how much is which, nobody can currently say. They may have gone quiet in the record, most likely both. In a ratio the rock has no intention of handing over. A second reading has also been gathering support, and it comes from asking which forms survived the first stage and which did not. The pattern that falls out has nothing to do with predators. What lasted were the fronds and the quilted sheets, the designs carrying the most surface for the least volume, the ones built to soak. That is precisely the shape that would do best if the thing running short was oxygen. The two readings sit closer together than they first appear. Animals that dig push oxygen down into sediment and pull nutrients out of the water. Animals that eat move carbon through a system that had never before had to account for being eaten. A world that acquires apatite is a world whose chemistry shifts underneath it, and separating the biology from the environment here may turn out to be a distinction the rock does not recognize, which leaves a fair question about the word itself. Is it right to call this an extinction? Every other event in this record has something to point at from outside the living world. An eruption, an impact, an ice sheet, a change in the composition of the air. This one has nothing but the neighbors. Nobody here was killed by the planet. They were crowded out, undercut, and in a small fraction of cases drilled through by the ancestors of everything that came after. It is the first entry in the record where the cause and the consequence belong to the same lineage, and it will not be the last. What it opened is not in doubt, The organisms that pulled that seafloor apart went on to build every seafloor since. Digging made a layer of ground with oxygen in it, which made room to live inside the seabed rather than on top of it. Eating put the first pressure on anything soft and slow to become hard or fast or hidden. And within a few million years, the shells and the eyes and the legs and the spines start appearing in the rock, together, in numbers that have unsettled everyone who has ever counted them. The garden did not survive contact with its own children, but the arrangement that replaced it is the one we are still living inside, a world in which nearly everything alive is either hunting or avoiding being hunted, and the seafloor is something to be dug into rather than stood upon. That new world arrived quickly, and it arrived crowded. What tends not to get said is how soon it began falling over, and how often and how thoroughly nobody counted it. A cup stands upright on the seabed in warm, shallow, sunlit water. It is about the length of a finger, open at the top, and its wall is doubled, an outer wall and an inner one with a narrow space between them, both drilled through with fine pores so that water passes in from the outside, crosses the gap and lifts away up the central cavity, carrying off whatever the animal has finished with. That is the whole of its life. It stands in the current, and it strains what goes past. Beside it there is another and another beyond that, and past those a low, crowded thicket of them, some finger length and some no larger than a thimble, packed together and cemented in place by a crust of lime that bacteria have laid down in the spaces. The whole assembly rises about as high as a kitchen chair. Further out along the shelf, the same structure repeats, mound after low mound, running for kilometers through water clear enough to read the bottom from the surface. The animal is called an archaeocyath. The name means old cup, which is close enough, and nothing like it has existed on Earth for 500 million years. None of this is large. The tallest of those mounds would not reach your waist, and a single archaeocyath would sit comfortably in your palm. What matters is not the size of the thing, but the fact of it, because these are reefs, and they are the first reefs the world has ever had. Bacteria had been building low domes for 2 billion years already. These are the first structures assembled out of animal skeletons. What a reef does for an ocean is roughly what a city does for a plane. It concentrates. The structure breaks the force of the water so that things far too delicate for open surf can live in the calm behind it. It puts up surfaces to attach to, crevices to hide inside, overhangs to shelter beneath. Every hole in it is a house, and because so much is packed into so little space, a reef holds life in quantities the bare shelf never manages. Somewhere around 520 million years ago, animals began constructing the physical fabric of an ecosystem out of their own bodies, and other animals moved into it. The arrangement ran for something under 20 million years. A little over 510 million years ago, the dating here is loose, and the honest window is several million years wide. The archaeocyaths go, not thinned out, gone. All of them on every shelf in the world, a group that had held a monopoly on the trade. How much else went with them is harder to fix, and the figures need their method carried alongside them. What gets counted in this part of the record is genera, which are groupings of related species rather than species themselves, and the estimates for how much of the marine record disappears across the interval run from about half up to 80%. At the sharpest point, at the close of the stage called the Botomian, the loss of genera passes 80% on its own. Measured against the events everybody knows the names of, that is not a modest number. It is one of the largest in the record, and the reefs did not simply collapse into rubble, they were taken over. What builds the mounds afterwards is the same thing that had built them before animals existed at all: bacteria, laying lime down in layers, raising structures with no skeletons in them and no rooms inside. The mats came back and resumed the work. Nothing with a skeleton took the trade up again for a very long time. Reef building of the kind the archaeocyaths had invented, animals making rock out of themselves and stacking it into a habitable structure, does not reappear in the fossil record until well into the Ordovician. The gap is roughly 40 million years. That figure is difficult to hold steady in the mind. It is more than 100 times the span our own species has existed. It is about the distance between us and the first whales that had lost the ability to walk. And it is worth setting beside the number everyone actually knows. The reefs also vanish after the extinction at the end of the Permian, the worst event in the whole of Earth's history, the one taught in every classroom. That gap runs to something like 5 million years. The forgotten one left the world without a single skeletal reef for 8 times as long. It also kept happening. For the remainder of the Cambrian, the shallow seas run through a cycle regular enough to have earned a name of its own. A trilobite fauna appears, spreads out across the shelf, diversifies into dozens of forms, and then at a boundary sharp enough that you can put a finger on it in the outcrop, it is almost entirely destroyed, and a different fauna moves in from deeper water offshore to take the space. That one spreads, diversifies, and is destroyed in turn. The intervals between the destructions were given a name in the 1960s, biomeres. In the rocks of North America, the cycle turns over 4 or 5 times. Something was coming up onto the shelf every few million years, killing the shallow water animals, and then withdrawing. The sharpest of these episodes carries an acronym that does it no favors, SPICE, and what it names is a movement in the carbon. Between roughly 497 and 494 million years ago, the carbon locked into limestone all over the world shifts, and shifts hard, in one of the largest excursions the period produced. A swing in that direction means organic material was being buried on an enormous scale rather than rotting away, and burial at that scale keeps company with water that has had its oxygen taken out of it. In the same rocks, there is evidence of something beyond simple oxygen loss. The deep water of those basins appears to have been carrying hydrogen sulfide, the gas that smells of rotten eggs and which is lethal to essentially everything that breathes. It sat down there in the dark, and periodically it came up over the shelf edge and spread across the shallows. That is what kept arriving. The ocean's own deep water, stripped and soured, sliding shoreward and then draining back over and over for tens of millions of years. None of this appears on the standard list. The archaeocyath collapse is absent from it, and so are the biomere boundaries, and so is the carbon swing, and so are the 40 million years in which no animal anywhere was able to build a reef. That absence has nothing to do with the events being small. In 2023, 40 years after the line was first drawn, the paleontologist Charles Marshall went back through the question and ranked the stages of the fossil record by the proportion of genera each one lost. The stages at the top of that list are not the famous ones. The Cambrian and the early Ordovician dominate it. Measured by how much of the living world it removed stage for stage, the most lethal stretch of the entire fossil record is the stretch with no famous name attached to any part of it. So there is a long span of seafloor, warm, well-lit, wide, running from a little over 500 million years ago to somewhere near 470, with nothing built on it. Lime mounds accumulate quietly, exactly as they had for 2 billion years before any animal had a skeleton. Trilobite faunas arrive and are erased and arrive again, but the cities are gone, and nothing alive can put one back. When reefs finally do return, well into the Ordovician, they come back built by other animals entirely. Corals, bryozoans, a fresh set of sponges, none of them descended from what went before. The world did not restore what it had lost. It invented the reef a second time out of different materials, having left the ground vacant for 40 million years. And then, About 25 million years after the new ones got going, the sea went out from under them. Where does an ocean go? It does not evaporate, and it does not drain, because there is nowhere for it to drain to. Water that leaves the sea has to be held somewhere else, and the only place on this planet large enough to hold any meaningful fraction of it is a continent, piled on top of one, frozen in a sheet. In the late Ordovician, the great southern landmass was sitting over the pole. Gondwana held what is now Africa, South America, Antarctica, Australia and India, all welded into one, and the center of the ice that grew on it lay across ground that is today the Sahara. There are glacial pavements in the rock of Algeria and Libya and Mauritania, scoured surfaces, grooved by stones dragged along under moving ice, in country that has not seen standing water in living memory. Snow fell there and did not melt, and was buried by the next year's snow, and compacted and stayed. Every cubic kilometre of it was a cubic kilometre that had come out of the sea and was not going back. Sea level fell by something on the order of 50 to 100 metres. On a steep coast, a drop like that moves the shoreline down the beach. On a continental shelf, it does something else entirely, because a shelf is almost flat. Take a sea floor that falls 1 metre for every kilometre travelled out from the land, which is steep for the shallow seas of that period, and 50 metres of drop removes 50 kilometres of seabed. The Ordovician world was covered in seas like that. Large parts of what is now North America, Europe and China lay under warm water shallow enough for sunlight to reach the bottom across their entire width, and it was there, in that thin sunlit sheet spread over the continents, that essentially everything alive was living. Those seas did not retreat, they emptied. Nothing that lived through it could have perceived it happening. The ice took hundreds of thousands of years to build, and a trilobite hatching on that shelf inherited water a fraction of a centimetre shallower than its parents, which is nothing at all to a trilobite. Run that for enough generations, and the shelf is gone, the reefs are standing in air, and the most crowded environment on the planet has become a plain of drying limestone the size of a country. It is the kind of catastrophe you could not have stood in the middle of and recognized as one. The figures usually quoted are 85% of marine species and around 53% of marine genera, and those two numbers are not independent of one another. The genus count is what was actually counted because genera are what the fossil record reliably preserves. The species figure is calculated out of it, using assumptions about how many species a vanished genus takes with it. That is not a criticism, it is simply how the arithmetic works. But nearly every extinction percentage anyone will ever quote at you is built this way, and the confident-sounding number at the front of it is usually resting on account of something else. The event also came in two parts, and there is nothing else structured quite like it anywhere in the record. The first pulse arrives at the start of the cold, and it takes the swimmers and the drifters, the animals of the open water, which had nowhere to go when the shelf seas shrank and the temperature dropped. Then, roughly 1 million years later, at the end of the Hernantian, the ice released. Sea level came back up, and the second pulse killed the survivors of the first. The first pulse killed by cooling, the second killed by warming. They belong to the same event, they sit 1 million years apart in the same sequence of rock, and between them they removed a little over half the genera in the sea. That is the version in the textbooks, and there is a serious case that it is wrong. In 2022, researchers David Bond and Stephen Grasby published a reading of the same interval in which the ice is not the killer at all. Their argument runs on mercury. When enormous volcanic provinces erupt, they put mercury into the atmosphere and it settles into marine sediment all over the world, leaving a measurable spike in rock of the right age. The spikes are there at both pulses. On their account, the sequence starts with volcanic warming near the beginning of the Hernantian, which expanded a body of oxygen-poor water already sitting in the ocean, collapsed the productivity of the surface and produced the first wave of losses. A second round of eruptions drove more warming, more oxygen loss, and the second wave. The two explanations do not merely differ over detail. One has the first pulse caused by cooling, and the other has it caused by warming, and they cannot both be right. Nobody disputes that the glaciation happened. The scoured rock is there. The sea level record is there. Cold water animals really do move toward the equator in the fossils. What is disputed is whether the ice was the cause or merely the company. There is a further argument running alongside over whether there were two pulses at all or one long one that the sampling has split in half. And there is a minority proposal that a burst of gamma radiation from a dying star stripped the ozone layer and did the killing from above. It has never gathered much support, and it is mentioned here only because it exists. Then there is the question this record keeps best, which is how long the world stayed empty afterwards. And the Hanantian gives two different answers depending on how the question is asked. Global compilations put the return to pre-extinction diversity at 15 to 20 million years. But in 2004, Krug and Patskowski went back to the same interval and did something the global curves cannot do. They took one paleocontinent at a time and corrected for how hard anyone had actually looked at it. Laurentia, the old core of North America, was back at its pre-extinction diversity within about 5 million years. 15 million years, or 5. The same extinction, the same rock, differing by a factor of 3 depending on whether the counting is done across the world or in one place. That gap is not a technicality to be tidied away. It is a caution attached to every recovery figure this record produces, and the reason an honest telling has to keep saying how each number was arrived at rather than simply handing it over. What refilled the shelves when the ice let go was not the water that had left them. Through the long freeze, the ocean had gone still and layered, the way a lake goes layered when nothing stirs it, and the water that rose back over the drowned shelf edge came up from underneath. It carried almost no oxygen. Across large stretches of the early Silurian world, the sediment of that time is black shale, fine, dark, organic rich mud that forms only where the bottom water is dead. If you had put a hand into that returning sea, it would have felt like any other sea. The same temperature, the same salt, the same light coming down through it as through any water you have ever swum in. There is nothing in the feel of water without oxygen to give it away. It simply does not hold anything that needs to breathe. All of it, the ice, the drop, the exposure, the drowning, the two killings a million years apart, turns on a change in the depth of the sea smaller than the height of a city block, applied slowly to a world whose entire population lived in the shallows. And the ocean did not steady itself afterwards. It came out of the Ordovician unbalanced, and for the next 25 million years it went on failing over and over through a period that almost every account until recently described as quiet. At one boundary in the Middle Silurian, around 433 million years ago, roughly 80% of the conodont species on Earth stop appearing in the rock. More than half the trilobite species go with them. Nothing in the sediment of that age suggests an impact or an eruption or anything whatsoever arriving from outside the ocean. It is called the Irrviken event, after a stretch of coast on the Swedish island of Gotland, where the rock records it cleanly enough to walk along. Conodonts are among the odder objects in paleontology because for the better part of a century they were the most useful fossils anybody had, and nobody knew what they were. They are small, a millimeter or two most of them, made of the same mineral family as our own teeth, and shaped like teeth. Hooks, blades, combs, little rows of points. They occur in marine rock of nearly every age across 300 million years in enormous numbers, And because their shapes change quickly and distinctively, they remain the finest instrument anyone has for dating a layer of seafloor. Entire careers have been built on them. And until the 1980s, when a complete animal finally turned up in Scottish rock, nobody could say what they had come out of. It was an eel, not literally an eel, but that shape, a slender, swimming animal a few centimeters long with very large eyes and the conodonts arranged in a basket inside its throat. They were teeth, after all. The animal had been eating with them for 300 million years and had left almost nothing else of itself behind. The graptolites, the other group cut down at these boundaries, are stranger to look at. On a slab of black shale, they appear as thin silvery lines, saw-toothed along one edge, sometimes branching, sometimes wound into a spiral, so close in appearance to pencil marks that the name means precisely that, written stone. They were animals nonetheless. Each of those saw teeth is a cup that held a small filter-feeding individual, and the whole line is a colony, thousands of them sharing a single skeleton, drifting through the open ocean instead of living on the floor of it. 3 times in the Silurian, the same thing happens to them. The Irrevecan comes first. Roughly 8 million years later, the Mouldy event arrives, and this time it is the graptolites that nearly go. The group reduced to a handful of surviving lineages while the carbon locked into limestone swings twice in 2 separate peaks, in one of the largest movements of the entire period. A few million years after that comes the Lau event, which takes the conodonts again, hard, and barely touches the graptolites at all. 3 collapses, 1 ocean, and each of them choosing differently. What connects them is temperature, and the record of it comes from the casualties themselves. The oxygen locked into conodont mineral as the animal grew carries a signature of how warm the water was around it, and at each of the 3 events that signature shifts sharply. The animals that died left thermometers behind, and the thermometers say the climate was moving every time. The whole Silurian runs to about 25 million years, shorter on its own than the gap the Cambrian reefs left behind them. 3 ocean-wide failures fit inside it, each sharp enough that a specialist can find the boundary in a cliff face by eye. And for most of a century this was the calm stretch, the period sitting between 2 of the events on the famous list, taught then and largely still taught as the interval where things settled down, plants got onto the land, and not much went wrong. The Silurian was never quiet. It was simply not being looked at. What none of the 3 has is a cause from outside. There is no crater. No large volcanic province has been pinned to them with any confidence, though the possibility remains open and the mercury work is ongoing. What the rock does contain at all 3 boundaries is the same signature the Ordovician left: black shale and water that had stopped holding oxygen. The immediate cause is not in dispute. The ocean lost its oxygen 3 times over, and the animals that needed oxygen died. What remains unsettled is what started it, and the leading candidates are all internal. Shifts in how the water circulated, changes in where the warm layers sat and where the cold ones did, the ocean rearranging itself. There is a sea doing exactly this now. In the Black Sea, fresh water arriving from the Danube and the Dnieper and half a dozen other rivers floats on top of denser salt water that came in through the Bosphorus, and the 2 do not mix. Below about 150 meters there is no oxygen at all, and there has not been for thousands of years. The largest body of dead water on the planet, lying beneath a busy, ordinary, well-fished surface. Send a light down into it, and you find wooden ships standing on the bottom with their masts still up, because nothing that eats wood can live down there to take them apart. That is one basin, with one narrow entrance, in one corner of one sea. The Silurian Ocean managed it across the world 3 times, which is the part of all this that sits least comfortably. Every event so far in this record has had something to point at. A waste gas that nothing could get rid of, an ice sheet, a continent drifting over a pole, the arrival of appetite. The Silurian offers an ocean that appears to have failed 3 times of its own accord, and then carried on as though nothing had happened. That ocean is the same ocean. It has not been replaced or refilled. It has only been for the whole of the time anyone has been watching it in one of its steadier moods. And through all of it, above the waterline, something was beginning that nobody at the time could have connected to the water. The bare rock of the continents was going green. A root finds a crack in the rock and goes into it. Where it enters, it is no thicker than a pencil, and it goes in for the ordinary reason that the water down there is easier to reach than the water anywhere else. Then it thickens. Wood is laid around it, ring on ring, and wood does not compress. The crack opens by 1 millimeter in a year, and then by 2, and the rock, which has been sitting unbroken since before anything on this planet had a backbone, comes apart along a line it did not know it had. That is the crude half of the work. The finer half happens at the root's own surface, where the plant and the fungus wrapped around it are both leaking acid into the mineral grains, dissolving them out of their crystal lattices and drawing what is useful up into living tissue. What gets left behind, once the useful part has been removed, is soil. Put a hand flat on the ground almost anywhere in the world today, and there is soil beneath it, and in most places the soil is deep. Deep enough in some river valleys to lose your whole arm in before you reach anything solid. Before the Devonian, there was almost none of it. You could have walked across most of a continent in the Silurian and touched nothing but bare rock, sand, gravel, and a thin green skin clinging to whatever stayed wet. The tree that did most of the changing is called Archaeopteris, and it was an odd combination of things. It made real wood, laid down in growth rings in the manner of a modern conifer, with trunks that you could not have got your arms around. It carried fern-like foliage. It reproduced with spores rather than seeds, which is to say it was still tied to damp ground in the way a fern is. And it went down. Its roots ran deep and branched hard, and where a forest of them stood, the rock beneath was being taken apart to a depth of meters rather than centimeters. The oldest forest floor anyone has found sits in Schoharie County in upstate New York, near a village called Gilboa. Fossil stumps were first uncovered there by a flood in the 1870s, and more came out of the ground during quarrying for a dam half a century later, upright, in place, rooted where they grew, about 385 million years old. Standing among them, in the exposure, is as close as anyone gets to being inside the first forest on Earth. Between the middle and the end of the Devonian, that forest spread across every continent, and the consequences of it went somewhere nobody would have predicted. Soil holds nutrients, phosphorus above all, the element that limits how much can grow in the sea. Rock does not release phosphorus easily. Soil, worked over by roots and acid and rain, releases a great deal of it, and rivers running through deep soil carry it downhill in quantities that bare rock never produced. Every year those rivers delivered more of it into shallow seas that had never had to deal with an oversupply of anything. What happens next is the same sequence that produces the dead zones at the mouths of large rivers now. The nutrient arrives, the algae bloom. The bloom is far larger than anything can eat, and it dies and sinks. Decomposition on the seafloor consumes oxygen, and if enough organic matter is falling, it consumes all of it. The bottom water goes dead. Black shale accumulates, and everything on the floor of that sea, in a world where nearly all the animals lived on the floor of the sea, has nowhere to go. The Devonian did this at least 3 times. The first, around 384 million years ago, is the least understood of them and comes with a large rise in sea level and the collapse of the barriers that had kept separate faunas apart. The second is the sharp one. Around 372 million years ago, at the boundary between the Frasnian and the Furmenian, two dark bands of shale are laid down in what is now the Harz Mountains of Germany, in a valley whose name has been attached to the whole event ever since, Quellwasser. Between those two black bands, the reef world of the Devonian ends. This is the one on the famous list. The late Devonian, fifth of the Big Five, taught in every classroom, and the one whose statistical significance the study that created the list specifically declined to certify. There is a reason it did not clear the line, and it becomes obvious once it is stated. That test was built to find spikes, single intervals in which the losses jump far above the intervals around them. The Devonian never produced a spike. It produced a long grinding down, spread across several stages and something like 15 million years, with the sharpest moment at the Quellwasser and heavy losses on either side of it. A test designed to catch one catastrophic interval is blind to a catastrophe that takes its time. The figure usually attached to it is around 40% of marine species, and the same caution applies as everywhere else in this record. The count was made on genera, and the species number is derived from it. The severity is genuinely argued over. What is not argued over is what happened to the reefs. Devonian reefs were the largest this planet has ever built. They were not made of corals alone, but of stromatoporoids, sponges that laid down massive layered sheets of limestone meters across, growing on top of one another until the structure ran for hundreds of kilometers. The best preserved of them is in the Kimberley in Western Australia, where the whole system now stands as a range of limestone hills in desert country, with the old reef front on one side and the drop into the deep basin on the other, and it can be walked end to end. Across the Quellwasser, that entire arrangement stops. The stromatoporoids go, the corals are cut down, and what takes over the reef sites is microbial, mounds built by bacteria laying lime in layers, with no skeletons in them and no rooms inside, exactly as had happened after the Archaeokiaths. The disorienting part is the direction of all this. In nearly every account of the world we tell now, trees are the remedy. They hold the ground together, they pull carbon out of the air, they are what gets planted when something needs repairing. The first time forests existed on this planet, the best available reading is that they suffocated the sea. That reading is not the only one, and it should not be handed over as settled. There is a live case that volcanism drove the Quellwasser, mercury spikes in the boundary rock, and a large igneous province erupting in Siberia at around the right time. And the mercury work has been getting stronger rather than weaker. The most honest position is probably that both are involved, that the forests spent 15 million years loading the system with nutrients until the shallow seas were running close to the edge of what they could oxygenate, and that eruptions then pushed a stressed ocean over. On the reef front in the Kimberley, the great sheets stop growing and the mounds take their place. The structure survives, standing in the desert, but nothing rebuilds it. Reef systems that match the Devonian for extent do not appear again until the age of the dinosaurs, which is to say that this recovery is measured not in millions of years, but in well over 100 million. The Cambrian reefs took 40. This one took the remainder of the Paleozoic and a good deal of what came after. And the forests, all the while, went on spreading and grew taller and pushed their roots down further, and the rivers running out of them carried more every year. Somewhere in the middle of all that, on the muddy edge of one of those rivers in water shallow enough to stand up in, something with 4 legs was hauling itself out onto the bank. For a while we can watch it. The animals of that moment are in the rock in East Greenland, in Pennsylvania, in western Russia, and the best known of them, a Acanthostega, had 8 fingers on each hand, not 5. 8, arranged in a paddle, on a limb with a shoulder and an elbow and a wrist, attached to a body that still carried gills in its throat and a fin along its tail. The hand had not settled on 5 yet, because nothing had yet told it what a hand was for. Then the rock goes quiet. For something like 15 to 20 million years after the close of the Devonian, across every continent, there are almost no land vertebrates in the fossil record. Not few, effectively none. The animals that had spent the late Devonian acquiring shoulders and necks and weight-bearing limbs drop out of view entirely, and what emerges on the far side when the record resumes are creatures already well on their way to being amphibians and reptiles, which means the whole of that transformation happened somewhere nobody could see it. Alfred Romer set the problem out in the 1950s and was blunt about it. There was a hole in the record precisely where the interesting part of the story should have been. The hole eventually took his name: Romer's Gap. What made it is called the Hangenberg, after a section in the Rhenish hills of Germany, and it sits at the Devonian Carboniferous boundary about 359 million years ago. The pattern is one this record has already established: a black shale laid across the sea floor, the same fine dark mud that forms where the bottom water has stopped holding oxygen. Then ice grows on Gondwana, the sea level drops, and the shallow shelves drain. The sequence in the rock is anoxia followed by withdrawal, and it happened worldwide. The most complete casualty of it is a group most people have never heard of. Placoderms were the armoured fish of the Devonian, head and shoulders encased in interlocking bony plates, hinged at the neck so the whole front of the skull could rotate upward when the mouth opened. They had no teeth. The largest of them, Dunkleosteus, closed instead on bony blades that sharpened themselves against each other every time the jaws shut, and its head armour alone ran well over a metre across. How long the rest of the animal was is currently being argued down from the older estimates, which is the ordinary business of the field. For roughly 70 million years, placoderms were in nearly every sea and river system on the planet, in hundreds of forms. At the Hangenberg, every one of them stops. The boundaries of the category have shifted since. Later workplaces some of the earliest members on the line that leads to modern jawed fish. So the group is now understood as a stage rather than a single branch. But the armoured animals themselves, the whole plated Devonian assemblage, end there and leave nothing behind them. What did it is less settled. In 2020, a team led by John Marshall reported something unusual from Boundary Rock in East Greenland. Land plant spores, preserved in enormous numbers, and a great many of them malformed. Spines grown in the wrong places, walls deformed, and some darkly pigmented in the way plants pigment themselves against strong ultraviolet light. The reading offered was that the ozone layer failed during a spell of rapid warming, and that what killed on land and in the shallows was sunlight. Alongside it, the same study found no mercury spike at the boundary, which means that unlike almost every other event in this record, there is no large volcanic province standing behind this one. That is a striking claim, and it should be handled as what it is: a recent result, published once and already challenged in print by other workers. The malformed spores are real. Whether ultraviolet light is what caused them, and whether that is what emptied the seas, is not yet something anyone should state flatly. The man who broke the gap open was not a professor. Stanley Wood was born in Edinburgh in 1939 and had no training of any kind. At 29, he decided he wanted to find fossils, and he spent 2 years working the shoreline at Wardy on the north edge of the city, going out in whatever weather, splitting rock and finding nothing whatsoever. Eventually, he went to the Royal Scottish Museum and asked what he was doing wrong. He was told, kindly enough, that he had spent 2 years looking at the wrong kind of rock. That is where most people would have stopped. Wood went back out. He taught himself by visiting the outcrops that 19th century collectors had made famous, and learned to read the signals, the colour of a weathered face, the way a particular bed comes apart under a chisel, the small dark flecks that mean bone rather than mineral, which you will not notice unless somebody has already shown you what they look like. Over the next 4 decades, he found 29 species new to science, 4 of which were named after him. He opened a shop in Edinburgh and sold fossils to fund the digging. In the Scottish borders, on a bend of the Whiteadder Water near the village of Churnside, there is an exposure called Willie's Hole. The rock is a grey siltstone, finely laminated, flecked through with mica so that a fresh surface catches the light and it splits into flat sheets. Split it in the right place, and the face you open has not been in daylight since the Carboniferous. There is nothing dramatic about the outcrop. You would walk straight past it. It is a low grey bank in quiet farming country, and it is Tournaisian, 350-odd million years old, sitting squarely inside the gap. Wood worked it. Out came fish and scorpions and plants, and then the thing nobody had been finding, tetrapods, land vertebrates from inside Romer's Gap, where for half a century there had been essentially nothing at all. The results were published in 2012. Timothy Smithson, Stan Wood, John Marshall and Jennifer Clack in the Proceedings of the National Academy of Sciences, describing tetrapod and arthropod faunas from 4 new Tournaisian sites in Scotland. Work across the Tweed Valley since has kept adding more material from the coast section at Bournemouth, a jaw from Tantallon, further finds at Coldstream. The gap is not closed, but it is no longer empty, and nobody can any longer say that nothing is known about what happened inside it. Stan Wood died in September of the same year the paper appeared. He was 72, which leaves the question of what was actually missing, because it turns out not to have been the land record. In 2010, Lauren Sallon and Michael Coates assembled a database of vertebrate occurrences, more than 1,200 kinds of animal from 66 localities, and ran it across the boundary. The long-term loss came to over half of vertebrate diversity. Then, in 2015, Sallon and Andrew Galimberti looked at what happened to the survivors and found the thing that reorders this entire chapter. For at least 36 million years after the Hangenberg, vertebrates stayed small. Not scarce, small. The oceans refilled, and they refilled with fish, and essentially every one of those fish would have fitted comfortably in a hand. The large-bodied forms did not come back, and nothing evolved into the space they had left. 36 million years is longer than the entire Silurian period. It is a stretch of time in which the seas of the world held no large animal at all, not because the large animals were being killed, but because nothing was able to become one. That is a different sort of emptiness from the kind this record usually reports, and it does not look like emptiness at all. Nothing about that ocean would have seemed wrong. It was full and busy and lit, with current and food moving through it. Everything in it was simply the size of your palm, and stayed that way for 36 million years, because that was what a fish was. And while the sea stayed small, the land went the other way. The animals that came through the gap, the ones out of the grey siltstone on the Whiteadder, walked up onto ground that was becoming something the world had never carried before, wet, hot, enormous, and built almost entirely out of trees. A pool of black water sits under the trees, perhaps 20 meters across, with no current in it and no ripple on it. The air above is thick and unmoving and smells of decay that is not quite happening. Something falls into the pool, a frond, a section of trunk, a whole tree eventually, and it goes under, and it stays there, and it does not rot away. The water has no oxygen in it. Whatever settles into that mud settles for good. Multiply that pool by a continent. The equatorial belt of the Carboniferous world was a single wet lowland running from what is now the eastern United States across Britain and into Central Europe and beyond, and for tens of millions of years the plant matter falling into it was buried rather than recycled. That is coal. Every seam of it anywhere in the world of that age is a stack of Carboniferous forest floor that never got taken apart. Burying that much plant material has a consequence that reaches the top of the atmosphere. Photosynthesis splits water and releases oxygen. The oxygen is normally consumed again when the plant decays. Stop the decay, and the oxygen stays out. Atmospheric oxygen in the late Carboniferous is estimated to have reached somewhere around 30% against today's 21% and possibly higher still, though the figure comes out of models rather than any direct measurement, and the models disagree with each other by several points. An atmosphere that rich does peculiar things to animals that breathe through tubes instead of lungs. Arthropods take oxygen in through openings along the body and let it diffuse inward, which sets a hard ceiling on how large they can get. Raise the oxygen and the ceiling lifts. There was a millipede in those forests, 2.5 meters long, wide enough that its trackways in the sandstone look like tire marks. There were dragonflies with a wingspan of 70 centimeters, about the size of a large hawk, hunting through the canopy on wings that could not support an insect that size in the air we have now. The trees themselves were not trees in any sense we would recognize. The tall ones were club mosses, relatives of the small, creeping plants that live on a modern woodland floor, grown to 30 or 40 meters, with trunks marked in diamond patterns where old leaves had detached. Their trunks were mostly bark. There was very little wood in the middle, just a thin core carrying water up, so that the whole structure was closer to a hollow column than to an oak. They grew quickly, reproduced once, and fell. Why so much of them accumulated is still argued. The long-standing answer was biological, that lignin, the tough compound in plant tissue, was new, and the fungi capable of digesting it had not yet caught up. More recent work has shifted the weight toward geography, that the coal belt sat on the equator in permanently wet basins that were sinking as fast as they filled, and that this alone will produce coal without anything unusual happening to the decomposers. The honest position is that both are still on the table. The first blow to that world came from the far south. Around 330 million years ago, ice began accumulating on Gondwana again, the beginning of a glaciation that would run for the better part of 100 million years. In the seas of the northern hemisphere, the effect was severe. The crinoid and coral assemblages of the early Carboniferous, which had been rebuilding steadily since the Devonian, were cut apart. It is the largest extinction of the period, and at least one recent assessment places its ecological impact above the end Ordovician, a single line of argument and one to hold lightly. But it indicates the scale of what is being discussed. The mechanism, where it has been examined closely, looks familiar: a warm interval inside the Ice Age and water that stopped holding oxygen. The forests survived that. They did not survive what came about 25 million years later. Around 305 million years ago, the climate over the coal belt dried. The continuous wet lowland broke up into separate patches of surviving swamp with dry ground between them, and the tetrapod record changes character immediately. In 2010, Sada Sani, Michael Benton, and Howard Falcon Lang went through it in detail and found the extinction rate among land vertebrates peaking, local diversity collapsing, and something appearing that had never been in the record before: endemism. Up to that point, the same animals turn up across the whole belt from one end of the tropical forest to the other, because it was one habitat and nothing was dividing it. Afterwards, they do not. Each surviving patch of wet forest develops its own set of species, distinct from the patch next door. It is the first moment in the history of land vertebrates when the answer to what lives here depends on where here happens to be. The point at which the terrestrial world stopped being one place and became many. The animals that suffered most were the amphibians. Their eggs have no shell and no internal water supply. They have to be laid in standing water, or they dry out and fail. An amphibian in a shrinking swamp is not merely inconvenienced, it is confined to whatever is left, and when the water goes, the lineage goes with it. The animals that did well had a different arrangement, and they had already had it for 10 million years without it mattering much. The amniota egg carries its own pond inside the shell, a set of membranes enclosing the developing animal in fluid, with a separate compartment for waste and another for gas exchange, so that the whole business of early development can happen on dry ground. The earliest known animals with it come from joggins in Nova Scotia, small lizard-shaped creatures about 315 million years old, found fossilized inside the hollow stumps of fallen club moss trees that they had dropped into and been unable to climb out of. There is a way of reading what happened next that is easy to reach for and slightly wrong. It is tempting to say that the amniotes won. They did not win anything. The world stopped supplying continuous swamp, and a reproductive arrangement that had been sitting quietly in the population for 10 million years, conferring no particular advantage, abruptly became the only workable way to be a land vertebrate across most of the available ground. Nothing improved. The conditions changed, and a feature that had been unremarkable became decisive. Into the fragments, and then out of them across the drying continent, went the lineage that leads to every reptile, every bird, and every mammal now alive. You were not laid in an egg, but you developed inside one of its membranes, because the amnion did not go anywhere. It is still there, in every mammal, doing exactly what it was doing 300 million years ago. The first 9 months you ever lived through were spent floating in a small private pond, sealed off from the outside world, for the same reason a lizard's egg is sealed, because the large ponds dried up, and the animals that carried their own came through, and the drying did not stop. The ice on Gondwana grew and shrank and grew again. The continents kept closing on one another, and by the time they had finished, there was a single land mass on Earth with an interior no rain could reach. What lived on it had already begun to change, quietly, unevenly, some 20 million years before the record shows anything going seriously wrong at all. How do you tell an extinction from a gap in the record? From inside the rock, they are identical. In both cases, the animals are present in one layer and absent above it. In both cases, the absence runs on for a while, and then something different appears. Nothing about the sediment announces which of the two has happened. The difference between a world that lost its animals and a world where nobody has yet found them has to be argued for from the outside, using evidence about how hard people have looked, and where and in what kind of ground. This matters more than it sounds, because every figure anyone has given you so far, every percentage, every recovery interval, every claim that a group stops, rests on somebody having decided that an absence in the rock was a real absence in the world. And the problem is that no amount of looking harder at the fossils themselves will settle it. You have to interrogate the looking. Nowhere is that argument sharper than at a boundary about 273 million years ago in the early part of the Permian. The American paleontologist Everett Olson spent much of his career on the tetrapods of the Texas and Oklahoma red beds, and he noticed something abrupt. The animals of the early Permian and the animals of the middle Permian are not variations on each other. They are different castes. Below, the ground belongs to the pelycosaurs, the sail-backed synapsids, of which Dimetrodon is the one everybody has met in a box of plastic dinosaurs, and which is not a dinosaur at all, but a member of our own branch, a closer relative of ours than of anything with feathers. Above, The pelycosaurs are gone, and the world belongs to the therapsids, the animals that will eventually produce mammals. And between the two, there is a stretch where the record thins to almost nothing. The same interval carries two names, and which one a specialist reaches for tells you what they think happened. Olson's gap, if the belief is that the rock is missing. Olson's extinction, if the belief is that the animals were. The case against it being an extinction is a good one, and it is not really about fossils at all. Nearly everything anyone has from the early Permian comes out of a handful of formations in Texas and Oklahoma. Nearly everything from the Middle and Late Permian comes out of European Russia and out of the Karoo Basin in South Africa. Set those two collections side by side, and of course they look like different worlds. They are different places, on a supercontinent large enough that its two ends carried different climates and different animals in the same century. What appears to be a world changing may only be a camera moving. For a while, that objection looked decisive, and it deserved to. What has happened since is that people have gone back at it with better instruments, counting at the level of species and genus rather than families, and applying several independent methods for correcting the unevenness of how the record was collected, and the drop is still there afterwards. It survives the correction. That does not make Olson's extinction a settled fact. It moves it out of the category of things that are probably an illusion and into the category of things that are probably real and not yet fully explained, which is a less satisfying place to leave it, but a more honest one. The likeliest driver, on current evidence, is the drying itself, a supercontinent finishing its assembly, an interior that rain could no longer reach, and a slow squeeze on everything that needed water to reproduce or to stay cool. The second event is firmer, and almost nobody has heard of it either. Around 260 million years ago, in what is now southwestern China, an enormous volume of basalt came to the surface across an area centered on the mountains of Sichuan. The Meishan Traps are named after one of those mountains, and by the standards of what this record has already produced, they are not the largest of their kind, but they were more than sufficient. In the shallow tropical seas of the time, the losses are severe and they are selective, falling hardest on the animals that had specialized into warm, clear, carbonate water. The most conspicuous casualties are the fusulinids, and they are worth a moment because of what they were. Single-celled organisms, one cell each, that had grown to the size of a grain of rice, and in the largest forms a good deal more than that, building coiled chambered shells that accumulated into limestone across the tropics. A single cell you could pick up between finger and thumb. The big ones go at the Capitanian and do not come back. Whether this counts as a mass extinction in its own right is argued. Some workers have made a serious case for putting it on the famous list, which would make it a sixth. Others read it as the opening phase of a longer decline that does not properly separate from what follows. The dating is good enough to say that it is roughly 8 million years before the end of the Permian, and not good enough to rule out a connection. 8 million years is a long warning. It is roughly the span separating us from the last ancestor we shared with chimpanzees. Set the three events out in order, and something appears that none of them shows on its own. Olson's at around 273 million years ago. The Capitanian at around 260, and then the end of the Permian at just under 252. 21 million years, three separate failures, each taking a different part of the world's living inventory, and each studied for decades as though it stood alone. Nothing alive experienced that as a sequence, because nothing lived long enough to, and nobody working the rock experienced it as a sequence either, for most of a century, because the three sit in different formations on different continents and were dug out by different people with different questions. It is only from a distance and only fairly recently that they line up into a shape at all. a world that had been failing in installments, roughly 10 million years apart, for 20 million years before the event everybody has heard of. What none of that establishes is whether it was a sequence in any meaningful sense, or three unrelated accidents that happened to fall in a row. Nobody has demonstrated a mechanism linking them. The eruptions in China have nothing to do with whatever dried out Texas, and neither of them made what came next inevitable. They are simply the last two intervals of an ordinary world. And about 8 million years after the second one, in what is now northern Siberia, magma began working its way upward into a basin filled with coal. Nothing about the beginning of it is visible. A sheet of molten rock, somewhere between a few meters and a few hundred meters thick, is moving sideways between two layers of sediment a kilometer or more underground. It follows the bedding because that is the easiest path, and it carries a temperature of around 1100 degrees. Above and below, the rock it has pushed into begins to bake. 2 kilometers of ground lie between it and the sky, and at the surface, if you were standing on it, there would be nothing at all to notice for a very long time. Ordinarily, that is the whole story. A hot sheet cools, the rock around it hardens into a baked rim a few meters thick, and nothing comes of it. But the rock this sheet has entered is a coal basin. Coal is buried forest. Heat it underground and it does not burn because there is no oxygen down there to burn with. It cracks. The long carbon chains come apart into shorter ones, and what comes off is gas, methane, carbon dioxide, a mixture of lighter compounds, in volumes far beyond anything the pore space can hold. The gas works upward through fractures, and where the pressure is high enough, it makes its own exit, blasting out a vertical pipe of shattered rock hundreds of meters across, running from the cooked seam to the open air. The sedimentary pile in the Tunguska Basin of Siberia contained coal, and beneath the coal it contained Cambrian salt beds, which give off compounds that attack ozone when they are heated. Into that pile, over something on the order of 1 million years, went one of the largest volumes of magma ever emplaced in the crust of this planet. Individual sills there run to more than 400 meters thick. The eruptions at the surface covered an area the size of Western Europe in basalt. And the eruptions are not the point. The measurements that matter came from the aureoles, the baked rims around the intrusions, and what they show is that the gas released by cooking the sediment amounted to somewhere between 4 and 9 times what the magma would have released on its own. The volcano was not the problem. What the volcano set fire to was the problem. The ocean can absorb an enormous amount of carbon dioxide. It does this continuously, and what neutralizes the acid produced is the slow weathering of rock on land and the dissolving of carbonate on the seafloor, both of which run at their own pace and cannot be hurried. It is the same arithmetic as rainfall and a river valley. A catchment that shrugs off a meter of rain spread across a year will flood catastrophically if it receives the same meter in a week. The total is not the thing that decides. What decides is the rate against the drain. How fast it arrived is now known with unusual precision, and the number comes from a hillside in eastern China. At Meishan, in Zhejiang province, the Permian-Triassic boundary is exposed cleanly enough to have been made the world reference section for it, and 5 thin beds of volcanic ash run through the sequence. Volcanic ash contains zircon, a crystal that traps uranium as it forms and then keeps time, because uranium decays into lead at a rate that nothing in nature can alter. In 2014, a team led by Seth Burgess dated those 5 ash beds. The killing interval comes out at about 60,000 years, with an uncertainty of nearly 50,000 on it, which is to say somewhere between roughly 10,000 years and roughly 110, and that is the best anyone can currently do. Everything else in this record is measured in millions. This one is measured in tens of thousands, which is the unit used for the last ice age, or for the arrival of people in Australia. or for the whole span of anything recognizably like modern human life. The largest extinction in the history of complex life is the only entry on the list that happens on a timescale a human archive could, in principle, have covered from beginning to end. What the carbon did to the water follows in order, and none of it is surprising. The ocean warmed, the same conodont teeth that recorded the temperature shifts of the Silurian record this one, and what they give for the equatorial surface ocean in the aftermath is somewhere around 40 degrees. Warm water holds less dissolved gas than cold water, and warm surface water sitting on cold, deep water does not mix, so the oxygen that was already down there was used up and not replaced. The carbon that dissolved lowered the pH, which made it harder for anything to build a shell out of calcium carbonate at exactly the moment when everything with a shell was already under pressure. And in the shallow seas, in places, something older took over. When oxygen goes, sulfur-reducing bacteria move into the space, and their chemistry is the chemistry that ran this planet before there was any oxygen in the air at all. The world that was driven down into the mud 2 billion years earlier and has been waiting there ever since. Their pigments are preserved in the boundary rock. For a while, in some parts of the ocean, the water went back to being what it had been before anything breathed. On land, what emerged from it is something the world has not produced since. If you had walked across the southern continents in the first few 100,000 years of the Triassic, from what is now the Karoo in South Africa, down over Antarctica, across to India and on into China, thousands of kilometers over a single joined landmass, you would have met, again and again and again, the same animal. Lystrosaurus was about the size of a large pig. Barrel body, short sprawling legs, a horny beak where the front teeth should have been, and 2 tusks pointing down from the upper jaw. It seems to have spent a good deal of its life underground. In the best studied early Triassic beds, it makes up between 90 and 95% of the land vertebrate fossils recovered. That is not 90% of the fossils of its own group. It is 90% of everything. Nobody is certain why. The burrowing may have sheltered it from heat and from air carrying less oxygen than ours. It may have been able to eat almost anything. It may simply have been in the right places when the places stopped mattering. What is not in question is the outcome. For a span comparable to the entire existence of our own species, the large animal fauna of an entire planet was, to a first approximation, one species. Whatever else you might have seen on that walk, insects, small reptiles, a few amphibians holding on in the wet ground, the large animals were the same animal, everywhere, from one end of the world to the other. The rebuilding was slow, and it was interrupted. Around 1.5 million years after the boundary, the temperature spiked again and then fell sharply, and the animals of the open water that had been diversifying fastest were knocked back down. Recovery in this record is not a curve, it is a series of attempts. The gaps it left are the clearest measure of what had happened. Reefs are absent for about 5 million years. A stable, complex ecosystem, one with the full range of body sizes and feeding roles filled, does not reassemble for 8 or 9. And there is no coal. Coal needs peat, and peat needs particular plants growing in permanently wet ground, accumulating faster than they rot. Somewhere in the crossing of that boundary, the world lost the ability to do it. There is no coal of early Triassic age anywhere on Earth. Not thin coal, not poor coal, none at all. The seams resume about 9 million years later, made by different plants, and full Permian levels of peat thickness and plant diversity do not return for another 13 million years after that. Which brings this event to the measure this record has been keeping all along. By kill count, nothing approaches it. The end Permian is the largest extinction in the history of complex life, and no revision of the numbers has ever come close to threatening that. By the length of the silence afterwards, it is fourth. 5 million years without reefs, 9 without coal, 20 before the forests were themselves again. These are enormous figures, and they are exactly what an event of this magnitude ought to produce. They are also shorter than the 40 million years the Cambrian reef builders left behind them, shorter than the 36 million years in which nothing in the sea was able to grow large after the Hangenberg, and a great deal shorter than the Devonian reef gap, which runs to well over 100 million years and remains the longest quiet in the entire record. That ordering is not a suggestion that the end Permian was mild. It was not mild. It is a statement about what the two measures are actually measuring. Counting the dead tells you how hard the world was hit. Counting the silence tells you how long it took to build the same kind of thing again, and those turn out to be separate questions with separate answers. The Permian world was destroyed and reassembled inside 20 million years. The Devonian lost its reefs and did not get them back until the age of dinosaurs. So the worst thing that ever happened to life on Earth is, by the measure this record keeps best, not the emptiest interval in it. It is the fastest, the most complete, and the most violently chemical. And the world came back from it more quickly than it came back from events that have no popular names at all. Which is the strange thing about measuring silence rather than severity. It does not reward how hard the blow landed. It rewards whatever it is that makes a particular kind of world difficult to build a second time, and nobody yet knows what that is. Out of the space came new animals, the first crocodile-line reptiles, the first flying vertebrates, and the first dinosaurs. Small, unremarkable, badly outnumbered, and going nowhere in particular for the next 20 million years. And then, around 234 million years ago, it began to rain. Rain has no business appearing in the geological record at all. It is weather, the most ordinary process on the surface of this planet, a thing that happens on a Tuesday and has gone by Thursday, running on a timescale that rock cannot resolve and does not care about. And yet in sediment on every continent, between about 234 and 232 million years ago, there it is. In the Dolomites of northern Italy, where the Triassic is exposed about as well as anywhere on Earth, it shows up as a change of color. Below, the rock is pale limestone, the accumulated skeletons of a shallow tropical carbonate platform, the kind of clear, still, low-nutrient water that builds reefs. Above, the pale rock stops and dark terrestrial mud and sand come in on top of it, washed off a land surface that had suddenly begun shedding material. The platforms drown in silt. The same signature turns up in China, in Argentina, in the Arctic, in eastern North America, a sharp increase in whatever the rivers were carrying, arriving in at least 4 separate pulses across those 2 million years. The cause is now reasonably well agreed. Out in the ocean west of Pangaea, an enormous volume of basalt was erupting onto the seafloor and building a plateau. The province is called Wrangellia, and pieces of it are now bolted onto the western edge of North America, in British Columbia and Alaska and on Vancouver Island. Carbon dioxide went into the air, the world warmed. Warm air holds more water, and the monsoon that ran over a supercontinent the size of Pangaea intensified until the interior stopped being able to dry out between seasons. 2 million years of that, not a wet decade, not a wet century, an interval comparable in length to the whole Pleistocene, every glacial cycle of the recent ice ages from the first advance to the melting of the last, and for all of it, the weather did not go back to what it had been. In the sea, the losses were considerable. Estimates for the Carnian run as high as 1/3 of marine genera, which is a figure to hold on to, because it is roughly the same as the figure for the end Triassic event 33 million years later, and only one of those two appears on the famous list. On land, something else was happening, and the clearest evidence for it is footprints. The Dolomites preserve tracks as well as they preserve rock, and in the sequences running through the wet interval, The pattern is unambiguous. Before it, dinosaur footprints are scarce to the point of near absence. The tracks belong to other things. After it, they are common. The animals themselves had already existed for a few million years, small and unremarkable. A minor component of faunas dominated by beaked reptiles and by the crocodile line. Something about the reorganized world suited them, and they went from marginal to ordinary in a span the rock can measure. Then, about 33 million years later, the supercontinent began to come apart. The Central Atlantic Magmatic Province is the largest volcanic province of its kind that anyone has identified, measured by the area it covered. It erupted as Pangaea split along the line that would become the Atlantic Ocean, and its remains are now scattered across 4 continents by the ocean that opened through the middle of them. Basalt in Morocco, in Portugal, in Brazil, and on the western side, the long grey wall of the Palisades on the Hudson River, which several million people look at from Manhattan without any particular reason to know what they are looking at. The chemistry that followed is by now familiar. Carbon into the air, warming, acidification, and oxygen leaving the water. About a third of marine genera go. Something over 46% of the genera present in the final stage of the Triassic do not appear in the first stage of the Jurassic, and the species figure usually quoted around 3/4 is derived from those genus counts rather than measured directly, as almost all such figures are. Among the casualties are the conodonts. After 300 million years, after surviving the Ordovician, the 3 Silurian events, the Devonian, the Hangenberg, the End Permian, and the interruption that followed it, after leaving their small tooth-shaped record in nearly every marine rock anyone has ever dated, the eel-shaped animals that carried them stop everywhere and do not resume. The other great casualty group was the crocodile line. And this is the part of the story that gets told backwards more often than not, because through the late Triassic, those animals were not the underdogs. They were more numerous than the dinosaurs, more varied in body plan, and occupied a wider range of roles. Armored plant eaters, long-snouted fish catchers, upright predators built on a frame that would look entirely dinosaurian to anyone who had not been told otherwise. If a naturalist had been standing on that landscape and asked which group was going to inherit the planet, the honest answer would have been the crocodiles. They mostly did not survive the eruptions. The dinosaurs mostly did. Nobody outcompeted anybody. That raises a question this record keeps putting in the way and never quite settles. Is it fair to describe any of this as construction? The word does not really fit, and there is no better one on offer. Nothing was built. 2 enormous volcanic provinces erupted 33 million years apart. The climate moved both times, and a large number of lineages that had been managing perfectly well stopped. What is left at the end of it looks, from a sufficient distance, exactly like a plan. A marginal group promoted twice in succession until it held every large-bodied role on land, and kept them for 135 million years. But there was no promotion. There was a sequence of removals and one lineage that happened to still be standing after each of them. 2 places then, and neither of them looks like anything. The first is a floodplain somewhere in the middle of the Carnian, and what you would notice is how unremarkable it is. It is raining. It rained yesterday. The ground does not dry out between one downpour and the next. The rivers run brown and high. The ferns and horsetails have taken every low place there is, and none of it feels like an event. It is simply the weather. It is the weather your parents had, and their parents, and every generation back beyond any possibility of counting. The second is a coastal plain about 33 million years further on, a few thousand years after the eruptions stopped, and what you would notice there is the space. There is a great deal of room in it. Whole categories of large animal that had been common are simply absent, and the ones still moving through the gaps are not obviously distinguished. Some long-necked plant eaters browsing at the tops of the cycads, a few upright predators, nothing that carries any sign of having been handed anything. That is what a handover looks like from the inside. There is no moment in it, and nothing announces itself. There is only a world in which certain things are no longer present, and other things that had been there all along, going about exactly the business they had been going about for 30 million years, while nobody paid them any attention. The world that grew into the space was warm and green and belonged to them. It also, about 18 million years after the handover, laid down a sheet of black mud across the floor of half an ocean, and then did it again, and then once more, on a pattern that repeats more precisely than anything else in this entire record. Of the 35 or so extinction events in the recognized record, exactly one has an impact behind it that anyone has been able to establish. 1. It is also the one everybody knows, which is understandable, since it is the one that removed the dinosaurs. But it has left the general picture of how extinctions work almost precisely backwards. The image most of us carry is of a world going about its business until something arrives and hits it. What the rock actually shows, over and over, at intervals across 500 million years, is a world that stops being able to breathe. The physical evidence is a rock you can put your hand on, and once you know what it is, it becomes difficult to see it as anything else. Black shale is fine-grained and dark, and it splits into thin sheets along the bedding. It is soft enough to leave a smudge on your thumb. Break a fresh piece, and it smells faintly of oil, and if you hold a flame to it long enough, it will burn, because a substantial fraction of what it is made of is the carbon of things that lived and then were not eaten. Ordinary seafloor mud does not look like this. Ordinary seafloor mud is grey or brown or green, because anything organic landing on it is taken apart within days by animals and bacteria that need oxygen to do the work. Black shale is what settles when there is nothing down there able to do it. The first of the three is around 183 million years ago in the early Jurassic, and its volcanism came from the breaking apart of Gondwana, enormous outpourings of basalt across what is now southern Africa, Antarctica, and Patagonia. The carbon signature it left in the rock is the largest of the three by a considerable margin. The ocean warmed, the water columns stopped turning over, the oxygen went, and black mud accumulated across the seafloor of northern Europe and beyond. Some of that mud is on the Yorkshire coast near Whitby, and inside it are pieces of fossilized driftwood, the trunks of monkey puzzle relatives that floated out to sea, waterlogged, sank into oxygen-free mud, and were compressed for 180 million years without ever being allowed to rot. The material is called jet. It takes a very high polish, it is light enough to wear comfortably, and in the middle of the 19th century, after the death of Prince Albert, it became the standard material for mourning jewellery across the British Empire. A great many Victorian widows spent their bereavement wearing the Tuarcian anoxic event around their necks. The second and third come in the Cretaceous, roughly 120 million and 94 million years ago, and they follow the same script. In the first case, the source appears to be the Ontong Java Plateau, an oceanic volcanic pile in the southwest Pacific so large that it is difficult to find anything to compare it with. In the second, the volcanism is Caribbean and Arctic. Both times carbon goes into the system, the world warms, the ocean stratifies, and black shale is laid down simultaneously in basins that had no physical connection to one another. And here the pattern does something it has not done anywhere else in this record. Neither of the Cretaceous events produced a mass extinction. There were losses. Plankton communities turned over. Some groups of shelled organisms went. The reefs suffered. But nothing on the scale of the Permian or the Triassic, and nothing that any tally would place among the great events, despite the fact that the machinery ran identically, and in the case of the Pacific Plateau, at a larger volume of magma than the Siberian traps? Nobody has a settled explanation. The suggestions are reasonable, and none of them is demonstrated. That a Cretaceous ocean already warm and already stratified was populated by things adapted to exactly those conditions. That submarine eruptions deliver less gas to the atmosphere than eruptions on land. That the carbon arrived more slowly relative to the drain. The honest position is that we do not know why the same process killed almost everything on 2 occasions and comparatively little on 2 others. And until somebody works that out, the connection between volcanism and extinction is a strong statistical association rather than a mechanism anyone fully understands. The association itself is not in question. In 2017, David Bond and Stephen Grasby, the same two who had made the case for volcanism in the Ordovician, published a review that worked through nearly 20 biotic crises between the early Cambrian and the end of the Cretaceous, asking of each one what stood behind it. Their conclusion was that the temporal link between large igneous provinces and at least half of the major extinctions of that span makes large-scale volcanism the principal driver. A later paper put it more flatly: 4 of the big 5 and every smaller crisis since the Permian sit alongside one. Everybody knows the asteroid. Almost nobody knows the machine, and the machine has run around 20 times. And this is where it stops being only a story about the past. Black shale is source rock. Bury it deep enough, 2 to 4 kilometers, at temperatures somewhere between 60 and 120 degrees. And the organic carbon inside it does not sit there indefinitely. It cracks in the same way the coal under Siberia cracked, except slowly and without any help. Over tens of millions of years, the long molecules break down into shorter ones, and what comes out of them is liquid. The liquid is lighter than the water in the pores around it, so it moves upward through whatever will let it pass, until it meets a layer that will not, and it gathers underneath. That is oil, all of it. Every field anywhere in the world is a volume of rock that happened to catch what leaked out of a buried, suffocated seafloor. The source rock beneath most of the North Sea is a late Jurassic mudstone laid down in water that had stopped holding oxygen. A very large share of what comes out of the Arabian basins was generated in the middle of the Cretaceous, in the same intervals as those 2 great anoxic events. The pattern holds worldwide. A small number of narrow slices of geological time account for a wildly disproportionate share of the planet's hydrocarbons, and those slices are the intervals when the ocean failed. Whatever is in the tank of the car outside came out of dead water. It was laid down before there were flowering plants, in a sea with nothing living on the bottom of it, and it has been down there ever since. So the count at the end of all this runs roughly as follows: 1 extinction in the entire record with a crater behind it, something close to 20 with a volcanic province behind them, and black mud in the middle. And in nearly all of those, the same 5 steps in the same order: carbon into the air, heat into the water, the layers stop turning over, the oxygen leaves, and a dark band settles onto the floor. 20 times near enough in 500 million years. There is a gorge in Umbria above the town of Gubbio, where the Cretaceous limestone is exposed in an unbroken sequence along a road cut, and a person can walk up through it in an afternoon. Low down there is a dark band about 1 meter thick, the black mud of the second great anoxic event, laid down in water with nothing alive on the floor of it. Higher up the same road, in rock roughly 30 million years younger, there is a different layer. It is pale and thin, and about 1 centimeter across, and what is in it did not come from this planet. The layer is grey or reddish depending on where in the world it is exposed, and it is about the thickness of a finger. At Gubbio, it sits between two beds of white limestone with a sharpness that is difficult to credit until it is in front of you. The rock below is crowded with the shells of single-celled plankton, dozens of species of them, and the rock a hand's width above is almost empty of them. Whatever happened between one layer of mud and the next. In 1980, a team including the geologist Walter Alvarez and his father, the physicist Luis Alvarez, measured what was in that clay and found iridium. Iridium is scarce in the Earth's crust because nearly all of what the planet started with sank into the core while the planet was still molten. It is not scarce in asteroids. The concentration in that centimeter was tens of times what the surrounding limestone carried, and the same anomaly turned up in Denmark and in New Zealand, and then in every section anybody bothered to test. The crater took another decade. It had, in fact, already been found, a buried circular structure 180 kilometers across, picked out of gravity and magnetic survey data collected by a Mexican oil company in the late 1970s by a geophysicist who noticed it, could not explain it, and had no reason to connect it to anything. It sat in the files. When somebody finally went looking for a crater of the right age and the right size, it was already on paper under a kilometer of younger sediment on the northern coast of the Yucatan, centered near a village called Chicxulub. The object was somewhere between 10 and 15 kilometers across, and what matters almost as much as its size is where it landed. The Yucatan platform is carbonate rock sitting on top of thick beds of sulfate, gypsum and anhydrite, the evaporated remains of old shallow seas. Vaporize carbonate and you release carbon dioxide. Vaporize sulfate and you release sulfur compounds that convert in the upper atmosphere into fine droplets. And those droplets are extremely good at reflecting sunlight and extremely slow to fall out. The dust settles within months. The sulfur stays up for years. The planet turns at something like 1,500 kilometers an hour at that latitude. 20 minutes either side of the moment it arrived, the object would have come down over deep ocean instead, into basalt, with almost no sulfur in it, and the reading that has developed over the past decade is that the outcome would have been substantially less severe. It is an uncomfortable thing to know, and there is nothing to be done with it. 3,000 kilometers north of the impact, in what is now southwestern North Dakota, there was a river channel connected to an inland sea. It was an ordinary place. Sturgeon and paddlefish lived in it. Filter feeders, unhurried, straining small things out of the water through fine combs of bone set in their throats. Seismic waves from an impact of that size travel through rock at rock's own speed, which put them under North Dakota in something like 10 to 13 minutes. Water in a confined basin, shaken hard from below, behaves the way water in a bath behaves when the side is struck. It piles up at one end and comes back. What came up that channel was not a tsunami. A wave crossing the open ocean would have taken many hours and could not have reached that place at all, but a standing surge in a shaken body of water, carrying sand and gravel and everything that had been living in it. The glass arrived within the following half hour. Rock vaporized and melted at the impact site had been thrown clear of the atmosphere on ballistic paths, condensed into small beads on the way up, and was now coming back down over the entire planet, re-entering, heating the upper air as it fell. In North Dakota, it came down into the water while the fish were still in it. And the fish, being filter feeders, did the only thing filter feeders do. The site was described in 2019 in the Proceedings of the National Academy of Sciences. More than half of the sturgeon and paddlefish carcasses recovered from that deposit have impact spherules lodged in their gill rakers, not resting on the outside of the animal, but in the combs, in the passage where water goes through, precisely where they would be if the fish had taken a breath while the glass was falling. If you had been standing on the bank, nothing about the morning up to that point would have told you anything at all. The first sign would have been the ground moving. not violently at that distance, but unmistakably for a minute or two. Then the water coming up the channel, and if you had looked up in the interval between the two, the sky would have begun to glow, horizon to horizon, as several million tons of returning debris heated the air it was passing through. This gives the event something nothing else in this record possesses. Everywhere else, the best available resolution is tens of thousands of years, and the honest answer to when is a window with an error bar wider than all of human history. Here the sequence runs: impact, 10 minutes, 13, 30. The rock at that site preserves less than an hour. The complication is that the world was already being interfered with. On the other side of the planet, in what is now Western India, the Deccan traps were erupting, on the order of 500,000 cubic kilometers of lava put out across the boundary interval, with all the carbon dioxide that implies. For a long time, the argument ran as a straight contest between the two, with reputations attached, and it did not resolve. What settled it, as much as it has been settled, was a study published in 2020 that took the temperature records preserved in deep-sea sediment and ran them against carbon cycle models to work out when the volcanic gas actually entered the system. The answer was that the major outgassing pulse from the Deccan began and finished distinctly before the boundary. It warmed the world by a few degrees in advance, and that warming had already reversed by the time the asteroid arrived. The extinction sits on the impact and nowhere else. The careful reading, then, is that the asteroid struck a world that had been given a hard time and had mostly recovered from it, and that the impact is what did the killing. The volcano is real, it mattered, and it was not the thing. Immediately above the clay, in sections all over the world, the pollen record changes character completely. Before the boundary, it is dominated by the pollen of flowering plants. Above it, for a few thousand years, it is dominated by fern spores, in some places overwhelmingly so. Ferns are what colonizes ground that has been stripped. They come back first at Krakatoa, first on the ash flats below Mount St. Helens, first in any burnt or buried place. The fern spike is the first thing the record shows growing again, and it is visible in the rock as a change in the color of the pollen. What happened afterwards is best recorded in a stretch of badlands east of Colorado Springs called Corral Bluffs, where the first million years of the Paleocene are laid down continuously enough to be read almost year by year. The mammals that come through the boundary are small, smaller than the ones that went into it. Within about 100,000 years, they have returned to something like their pre-extinction size. By 300,000 years, there are animals the size of a large dog, and palms are growing. By 700,000, there are larger ones still, and walnut relatives in the flora. Each jump in animal size arrives alongside a jump in what the plants were offering. Mammals had been on this planet for about 150 million years by the time the asteroid came. That is not a short apprenticeship. It is longer than everything that has happened to the group since, and it covers the whole of the Jurassic and the whole of the Cretaceous. In all of that time, the largest mammal anyone has ever found was roughly the size of a badger, not for lack of capacity. Within 10 million years of the boundary, there were mammals the size of a rhinoceros, and the group had already produced whales, bats, primates, and horses. The capacity had been sitting there the entire time. What had not been available was the space. Every large-bodied role on land, browser, grazer, pursuit predator, ambush predator, was occupied, and had been occupied continuously by something else for 150 million years. The rooms were taken, and then, over the course of an afternoon and the years of cold that followed it, they were not. What came next was 66 million years of a planet with mammals in the large roles, which is the world we were born into and which looks, from the inside, like the ordinary arrangement of things. It was not a calm 66 million years. The losses are simply quieter and less well attended. and the first of them arrives about 10 million years in at the bottom of the ocean among organisms too small to see without a lens. 2 or 3 kilometers down, on the floor of the deep ocean, in permanent darkness and permanent cold, there is a single cell about the size of a grain of sand. 100 of them would sit comfortably on your thumbnail. It has built itself a shell out of calcium carbonate, a series of chambers, each slightly larger than the one before, coiled or stacked according to species, and it lives there quietly, putting threads of protoplasm out through pores in the wall to gather whatever drifts down from above. There are thousands of them on any square meter of abyssal sea floor, and there have been for a very long time. They are also the finest recording instrument this planet has ever produced. The oxygen locked into the carbonate as the shell grows carries a signature of the water's temperature, and the carbon in it carries a signature of what the ocean's chemistry was doing. The same trick the conodont teeth performed for the Silurian, except that these organisms are still alive, and the record runs unbroken from the deep past to the mud that settled last week. About 56 million years ago, a great many of them stop. The interval is called the Paleocene-Eocene thermal maximum, and it is the sharpest warming event in the whole of the Cenozoic. An enormous quantity of carbon entered the ocean and atmosphere over something like 6,000 years. Global temperatures rose by perhaps 5 to 8 degrees. The deep ocean warmed and acidified, and the carbonate on the seafloor began dissolving in places where it had been accumulating for millions of years. The deep-sea foraminifera lost something between 1/3 and 1/2 of their species, the largest extinction among them in 93 million years, and one that never fully reversed. On land, the response was almost the opposite. Mammals dispersed between continents on a scale they had not managed before, and the first primates, the first horses, and the first even-toed hoofed animals turn up in North America within a few tens of thousands of years of one another. Where the carbon came from is still argued. Methane frozen into seafloor sediment, thawing and releasing. Volcanism in the North Atlantic as Greenland separated from Europe, burning peat, thawing polar permafrost. Probably more than one of them in a sequence nobody has yet been able to order. The comparison that gets drawn most often, and the reason the event is studied as hard as it is, concerns the rate. Current estimates put the carbon released during that warming at something like 3,000 billion tons, delivered across roughly 6,000 years. The figure generally used for the total human release on the trajectories currently in play is around 5,000 billion tons across about 500. That is the whole of the comparison. It is the closest analogue available anywhere in 66 million years, and it ran about 20 times slower. Then the world began to cool and kept cooling in steps. The largest of the steps arrives at about 34 million years ago, and it is permanent. Carbon dioxide had been declining for tens of millions of years, and somewhere in that decline it crossed a line. Ice began to accumulate on the Antarctic continent and did not melt in the summer, and once enough of it had gathered, its whiteness kept the continent cold enough to hold what it had. Global surface temperatures fell by 3 to 5 degrees. The deep ocean cooled sharply and has stayed cool ever since. Before that, Antarctica had forests on it. The pollen is in the sediment cores, southern beach, the same group of trees that still grows in Patagonia and in New Zealand, and that you can walk through today in the rain on the western side of the South Island. Afterwards, apart from some warmer intervals, it has had ice. In Europe, the consequences were sudden enough to have been noticed and named more than a century ago. In 1910, the Swiss paleontologist Hans-Georg Stellin looked at the mammal faunas either side of the boundary and called what he saw La Grande Coupure, the Great Cut. Roughly half of the mammal genera of Europe disappear inside 1 million years, and what replaces them arrives from Asia across land that the falling sea had exposed. There is an equivalent turnover in Central Asia that goes by the name of the Mongolian remodeling. Among the losses in the sea are the last of the archaeocetes, the long-bodied early whales that still had recognizable hind legs. The cooling continued in further steps, and one of them, around 14.5 million years ago, followed a warm interval about 3 degrees above the present and brought East Antarctic ice back to something like its modern extent, with losses among marine and land faunas that have never been given a memorable name and are usually referred to simply as the Middle Miocene disruption. And then something happens that has no parallel anywhere else in this record. Between about 6 million and 5.33 million years ago, the Mediterranean dried out. The connection to the Atlantic closed slowly as Africa pushed north into Europe and the seaways through what is now southern Spain and northern Morocco shut. The Mediterranean loses far more water to evaporation than its rivers bring in. Without the Atlantic topping it up, the arithmetic runs one way only. The basin fell. Salt precipitated out as it went. The deposits under the Mediterranean seafloor run to 2 or 3 kilometers thick in the deep basins, which is a volume of salt difficult to hold in the head. Standing on the floor of it, you would be somewhere between 3 and 5 kilometers below the level of the world's oceans. The air around you would be hot and dense and hard to work in, the way the air is at the bottom of a very deep mine. There would be shallow hypersaline lakes in the lowest places, and salt flats, and the mouths of enormous dry canyons where the rivers had cut down to meet the new base level. The Nile carved one of those through Egypt, and it is still there, buried under later sediment, running beneath the city of Cairo. It lasted several 100,000 years. Then the Atlantic came back through at Gibraltar, and the basin refilled. How fast it refilled is one of the genuinely open questions of the last 2 decades. One widely cited reconstruction has the water arriving as a megaflood, most of the volume delivered in under 2 years, with the level rising by as much as 10 meters a day. That model has been under sustained challenge recently, and the case against it has been getting stronger. It may have been a flood. It may have been a long, unspectacular trickle over thousands of years. The rock has not yet decided. The last of the Cenozoic losses is also the most recently recognized. In 2017, a group led by Catalina Pimiento went through the fossil record of large marine animals, whales, seals, sea cows, seabirds, turtles, sharks, and found that around 36% of the genera present in the Pliocene do not appear in the Pleistocene, at roughly 3 times the background rate for the era. It is recent work, and it should be held as recent work. The largest shark that has ever lived is usually attached to that event, and the attachment does not hold. When the fossil record of Otodus megalodon was gone through carefully in 2019, discarding every occurrence that could not be verified, the youngest reliable specimens came out at about 3.5 million years, more than 1 million years before the megafauna losses. The people who did that work said so plainly. Whatever finished the largest shark, it was not the thing that finished the sea cows and the walruses. 2 separate events, close enough together in a record this coarse to have been read for decades as one. Something in all of this runs opposite to expectation. The Cenozoic is the best recorded stretch of time in the history of the planet. The deep sea cores are continuous. The dating is good to within a few thousand years in places. The chemistry can be read almost layer by layer, and the arguments are not fewer than they were back in the Cambrian. They are more numerous and sharper and better attended because there is finally enough evidence for people to disagree about in detail. By around 2.5 million years ago, the world had arrived at something recognizable. Antarctica under ice, Greenland beginning to follow, grasslands across the continental interiors, the tropics narrowed, and the whole system swinging in and out of glacial cycles on a rhythm set by the shape of the Earth's orbit. The whole of that descent from the hot peak of the Eocene down to the world we were born into comes to a fall of roughly 12 or 13 degrees in the global average, spread across 50 million years. That works out to about 1/4 of a degree every million years, a rate so slow that nothing which lived through any part of it could possibly have detected that anything was changing at all. And then, on the eastern side of Africa, in open country that existed because the world had cooled and dried, something began making sharp edges out of stone. How do you measure something you are standing inside of? Every other event in this record shares a property that is easy to overlook because it belongs to all of them at once. They are finished. The oxygen catastrophe has an end date. The Handenberg has an end date. The Devonian, which took 15 million years about it, eventually stopped. Reading extinction out of rock depends entirely on having the layer above as well as the layer below, on standing outside the thing and measuring its width. There is one entry where that is not available, and it is the part of this record where the honest approach is to lower the claims and give the dates. In Australia, the sequence is tight. Sediment cores from lakes and from the seafloor off the coast preserve the spores of a fungus called Sporomiella, which grows only on the dung of large plant eaters, and the quantity of it in the mud is a direct measure of how many large plant eaters were walking around. That signal is high and steady from 150,000 years ago onward. Then, between about 45,000 and 43,000 years ago, it collapses. Diprotodon, a marsupial the size of a rhinoceros, short-faced kangaroos 2 meters tall, a flightless bird heavier than a man, a marsupial predator with shearing teeth. All of them gone inside a couple of thousand years, in a window that arrives within a few thousand years of people spreading across the continent, and with no correlation to 120,000 years of climate swings that the same cores record perfectly well. In the Americas, the picture used to look similar, and it no longer does. The old account had people crossing from Siberia and arriving south of the ice around 13,000 years ago, with the mammoths and the ground sloths and the saber-toothed cats going within a few centuries of their arrival. That account is finished. At White Sands in New Mexico, there is a set of human footprints preserved in the mud of a dried lake bed, and the first dating of them, published in 2021, put them between 21 and 23,000 years old. The result was contested, as it should have been. It has since been confirmed twice by independent methods: pollen from Ice Age conifers, quartz grains from the sediment, and then lake mud dated by a third technique, all landing in the same window. Pleistocene animal tracks run through the same surface, interleaved with the human ones. Which means people and megafauna shared North America for roughly 10,000 years before anything went extinct. Not a few centuries, 10,000 years. What went, when it finally went thoroughly. Mammoths, mastodons, ground sloths the size of elephants, glyptodonts, short-faced bears, camels, and horses. Horses had evolved in North America. They had spread from there into Asia across the land bridge, and around 11,000 years ago they disappeared entirely from the continent that produced them, and did not come back until Spanish ships carried them across the Atlantic in the 16th century, which means that every Mustang you have ever seen is an animal that came home. Madagascar breaks the pattern in the other direction. The island's giants, elephant birds 3 meters tall, lemurs the size of gorillas, pygmy hippos, crashed within the last 1,000 years or so. But the evidence for human presence goes back much further, with cut marks on elephant bird bone dated to several thousand years earlier, and the current reading is that people and megafauna shared that island for something like 9,000 years with very little happening at all. Something changed late. What changed is argued over. The elephant birds laid the largest eggs any animal has ever produced, over 30 centimeters end to end, holding about the same volume as 150 hens' eggs, an object you would need both hands and some care to lift. Whole ones still turn up in the coastal dunes. New Zealand is the one case where nothing is complicated. Polynesian settlers arrived in the late 13th century. There were 9 species of moa, the largest standing 3.5 meters with the neck up, and every one of them was gone between about 1380 and 1445, inside roughly 150 years. Haast's eagle, the largest eagle that has ever lived, which hunted them, went with them because there was nothing else on those islands big enough to keep it fed. Set the 4 together and the tidy version does not survive. 2 of them are fast and tightly coupled. In the other 2, people and large animals shared the same ground for thousands of years, and then something shifted. The coincidence with human arrival is real everywhere. The mechanism plainly is not the same everywhere. And the interesting question is no longer whether people were involved. It is why the same arrival produced a collapse inside 2,000 years in one place and 9,000 quiet years in another. And nobody has a settled answer to that. The candidates are the obvious ones. How many people, arriving how quickly, with what equipment, into what climate, meeting animals that bred how fast. The record is not yet fine enough to separate them. After that, the losses stop being a pattern and start being individuals with dates attached. The moa are the earliest of them we can name, and the last of them died sometime in the 15th century, in a country where nobody was writing anything down. The aurochs were the wild cattle of Europe, bulls standing up to 1.80 meters at the shoulder, black with a pale line down the spine, the animal painted on the cave walls at Lascaux, and the ancestor of every cow now alive. They had ranged from Britain to Korea. By the middle of the 16th century, there was one herd left in a stretch of forest at Equator, west of Warsaw, and it belonged to the Polish crown. The crown looked after it. Hunting was stopped. Gamekeepers were assigned to the herd and exempted from local taxes in exchange for the work, which consisted mostly of keeping fields open so the animals had grazing and keeping the villagers' cattle away from them. It is, as far as anyone can tell, the first thing in European history that would now be called a conservation program, and it was run by men who had no framework for what they were doing beyond the fact that the king wanted the animals kept. They also counted. The Royal Survey of 1564 records 38 animals. The counts after that go down. By 1620 there was 1, a female, and she lived another 7 years and died in the forest in 1627 of natural causes, with people watching. There is no drama anywhere in that record. There is a series of numbers, written down at intervals by men doing their jobs, and the numbers get smaller. Georg Steller was the naturalist on a Russian expedition that wrecked on an island in the Bering Sea in the winter of 1741. The survivors spent the winter there and ate the animals in the shallows to stay alive, and Steller, who was a careful man in a bad situation, wrote them up, 8 or 9 meters long, perhaps 10 tons, no teeth at all, grinding kelp between horny plates, in water too shallow to submerge in, slow and unafraid, and easy. The survivors got off the island and reported what was there. Fur hunters followed. The last confirmed animal was killed in 1768, 27 years from the only scientific description ever written to the end of the species, and everything anyone knows about the living animal comes from one man who was starving at the time. The passenger pigeon was, by most estimates, the most numerous bird on the planet. Flocks in the early 19th century were described as taking hours to pass overhead and breaking limbs off the trees where they roosted. The last of them died in a cage at the Cincinnati Zoo on the 1st of September 1914. Her name was Martha. Somebody who had watched the flocks come through as a child could have read the notice of her death as an old man. And the last thylacine died at the Beaumaris Zoo in Hobart on the 7th of September 1936. The animal has been called Benjamin for most of a century and described as male. Work published in 2022 established that both of those are wrong. It was a female, and the name was attached afterwards by someone who had not been there. There is a set of figures from a study published in 2018 which measured the total mass of living things on Earth and divided it up. They are given here as they stand. By weight, humans make up about 1/100% of all life on this planet, a rounding error against the plants and the bacteria, which between them account for very nearly everything. Of the mammals, humans and the animals humans keep, cattle, pigs, sheep, goats, come to roughly 96% of the total mass. Every wild mammal in the world, every whale and elephant and bat and mouse and deer makes up the remaining 4. Livestock outweigh all the wild mammals and all the wild birds on Earth combined by something like 10 to 1. That is where the count stands, at the point where the record runs out, which is to say now. 2.5 billion years of it, an ocean rusting because something had started releasing a gas it could not use, ice at the equator, a world ended by appetite, 40 million years without a reef, the sea going out from under a shelf, 3 failures in a period everybody called calm, roots breaking rock and drowning the ocean downstream, 36 million years in which nothing could grow large, 60,000 years under Siberia, 2 million years of rain, an afternoon in the Yucatan, and a long cooling into the world we were handed. Somewhere around 35 events, one with a crater. Around 20 with a volcano behind them, one caused by trees, one caused, as far as anyone can tell, by nothing arriving at all, and one still open. There is something to sit with in the fact that any of this can be known. None of it was recorded deliberately. The planet keeps nothing on purpose. It buries things unevenly and forgets them, and the parts that survived did so through accidents of chemistry and geography that had nothing to do with anyone's intention. Every creature in this record died without knowing what was happening to it. The trilobites on the draining shelf did not know the ice was coming. The last placoderm did not know it was the last. The female in the Polish forest did not know she was a species. We are the first thing on this planet that has been able to see any of it. Not because we are especially clever, since the reading is slow and much of it stays wrong for decades at a stretch, but because we arrived late enough for the whole thing to be underneath us and stayed curious long enough to dig. It is a strange inheritance. Almost everything we know about the Earth is something the Earth had no interest in telling us, recovered out of mud that was never meant to be read. And what we hold, when we sit with it, is not a list of endings. It is the shape those endings make, which is something that none of the participants ever got to see. Because the shape is this: every silence in this record ended. The ocean that rusted came back. The ice that reached the equator melted. The reefs that went unbuilt for 40 million years were eventually built again by something else entirely. The seas that lost their oxygen got it back 3 times in the Silurian and twice in the Devonian, and again in the Jurassic, and twice more in the Cretaceous. The world that held no coal for 9 million years held coal again. The oceans that carried nothing bigger than a hand for 36 million years carried whales in the end. Every gap in this record has a top to it. None of that was owed to anyone, and none of it happened for anyone's benefit. It happened because the systems that broke were never the only systems available, and because there was always something in the margins, small, unimpressive, doing badly, going nowhere in particular, that turned out to be able to live in what was left. That is the one consistent finding across 2.5 billion years. Not that life is resilient, which is a word that flatters us. something narrower and stranger than that. The things which inherit are almost never the things that were doing well beforehand. What the record cannot tell us is how long any single silence lasts. They have run from 5 million years to well over 100, with no dependable relationship to how bad the event was, and nobody has worked out why. It does not predict. It is a set of endings read backwards by an animal that turned up for the last thin layer. But it does say one thing, and the thing is not small. So far, in 2.5 billion years, not one of the silences has been permanent. Every one of them filled. The seas came back. The forests came back. The empty rooms were taken by whatever had been waiting at the edges, and the world went on being a world. It is doing that now, under the ice and in the mud at the bottom of every pond, and in the dark of your own body. The survivors of the very first catastrophe are still going quietly about their work, as they have for 2 billion years, with no idea at all what they came through. The Earth does not hurry. It does not remember, and it has never once failed to fill a space.